In this problem, we are given the following circuit diagram here. We are also given that our phasor current is I of B is equal to 5 with an angle of 45 degrees. Our I of B is going to be this right here. Now we need to find the following phasor values. We need to find I of A, I of C, and V of G. That's going to be this value right here, here, and here. So looking at these, I can plug in what I know. For I of B, we know we have a 5 with an angle of 45 degrees. Now for here, we can find our I of A, and we're going to do this with voltage. If we look at our I of A and we look at our I of B, we can see that these currents are in parallel. That means the voltages are going to be in parallel. So the voltage for A is going to be equivalent or equal to the voltage of B. Since these are equal, if we find the voltage of B, we know the voltage of A. And then we can use Ohm's law to find the current. So now we're going to look for our V of B. In doing this, we're going to say that our V of B is equal to, and we know to find voltage, we're going to use current times resistance, or in this case, impedance, since we have a capacitor right here. Now our current we know to be 5 with an angle of 45 degrees. And this is being multiplied by our impedance of 15 ohms and our J negative 15 ohms. So we're just going to add these two together since they are both impedances. We cannot combine them though. That's very important to not do because the negative J15 is an imaginary number. So in doing this, we can either convert one of these to phasor form or the other one to rectangular form. We can't multiply them together when they're in two separate forms. So the easiest thing, if they're being multiplied together like this, is, for me, at least from my opinion, to convert our rectangular form to the polar form. That way we can multiply the numbers and then add the angles together. So to do this, we are going to use a Vmax and set this equal to the square root of our real number squared plus our imaginary number squared. That's going to give us our Vmax. To find our angle, we're going to set theta equal to a tangent of -1 with our I over R inside of here. And if we do this, we are going to get approximately 21 with an angle of -45 degrees. Now, if we look in the notes, under extra notes, I think, also that's linked below in the description, we are going to multiply our constants together, so we'll have 5 times 21. And this is going to give us that our V of B is equal to approximately 105. Now we're adding these two angles together, so we're going to get 0 degrees here. This is our V of B in phasor form. Now V of B is equal to V of A, so we're going to write this here. And now we need to solve for the current of A, which is I of A. I of A is equal to the voltage of A over the impedance, so we're going to have Z of A. Now when we write this out, we're going to have 105 with an angle of 0 degrees over our impedance, and our impedance at the I of A right here is going to be 25 plus J25 because we have our inductor and resistor. We're going to convert the denominator into the polar form, so we're going to use the equations that we wrote out here to do so. And if we do this, we're going to get that our denominator is equal to approximately 35 with an angle of 45 degrees. Now remember, we are dividing the numbers and then we are subtracting the denominator from the numerator. So we will have 105 divided by 35, and this will give us approximately 3, and our angle subtracted will give us an approximate -45. So for part I of A, we're going to have 3 as our magnitude and an angle of -45 degrees. Now we are going to solve for our I of C. For our I of C, we know that we have our initial current. This is basically the initial current before it flows through the system. When it flows through the system, it's going to go downwards and it's going to go to the right. So we're going to have to add these currents together because it splits in parallel at this node. Well, we're going to have to do the same thing for the current running through the long stretch up top right here, because we have a node right here and it splits in parallel like this. So we need to add these currents together. We're just going to call this current I of 1. We know that our I of 1 is equal to the current below, which is our I of B, and we know our I of B to be 5 times the square root of 45. Now we are going to add to this the current that is flowing against it. And since it's flowing against it like this, it's actually going to be a negative. So it's going to be a plus -2 with the angle of 45 degrees. So now we can solve for this. But to solve for it, we need to put it in the rectangular form, since we are really subtracting two things together. And to use our angle form, we're going to have the number, parenthesis cosine angle, plus j times the sine angle, and this is all in the same parenthesis. And if we plug our polar forms in, we're going to get this as our answer. So now we can combine like terms, and then we will have approximately 2.12 for our number, and then a j times 2.12 for our imaginary number. And this is going to be equivalent for our I of 1. Now, our I of 1 is not the end current that we want to find. This is just one of the currents. We are going to add our I of 1 to the I of A, because remember, the current I of C splits in these directions. So we will say that our I of C is equal to our I1 plus our I of A. We recently just found our I of A, that is what is right here, but we need to convert this into the rectangular form, again because we are adding these together, and then we're going to plug this in for our I of 1. And if we do that, we are going to get this as our new equation. From here, we can see that we can cancel out our j's because they are both negative, and then we're just going to combine our two real numbers. So from this, we are going to get that our I of C is equal to approximately 4.24 plus a j times 0. And this is our rectangular form. Now we want to convert it back into the polar form. We're going to use this equation right here. And just by looking at it, we can really see that our I of C is just going to equal 4.24 as our magnitude, and we are not going to have an angle, or we can say that our angle is 0 degrees. So when we plug this in here, we're going to write 4.24 for our magnitude at an angle of 0 degrees. And that is how we would solve for I of C. For our V of G, we are going to use a formula that we have previously gone over in Intro to Circuit Analysis, where we have our I of C set equal to the voltage over resistance. This is like an expanded form of Ohm's law. You can think about it like that. And in solving this, we are going to say that our I of C is equal to the voltage. However, we have this V of G and our V of A right here over our 5 ohm resistor, and that is how we are going to write it. So our equation is going to look something like this. This is equivalent to our I of C, and it's very important that we understand this. From here, we can just plug things in. So we know that our I of C is 4.24 with an angle of 0 degrees. We can multiply our 5 into this so that we don't have a denominator. So we'll have this by 5, and then we can add our V of A. So we will have a plus, and we know that our V of A is this value right here. So we are going to add this in as 105 with an angle of 0 degrees. This is all equal to V of G. Now, after we multiply this in, because our angles are both 0, we can just add the magnitudes together. And if we do all of this, we are going to get a magnitude of 126.2 with an angle of 0 degrees for our V of G. And that is going to be the answer for our V of G. And that is how you would go about solving this problem. If you want more network analysis problems, there's a playlist in the description, and if you want notes that cover this entire material or the entire coursework for this class, they will be in the description as well below the like button.